In this video, we are going to define what it means for a function to be of exponential order. And this is relevant because we're interested in knowing which functions have Laplace transforms. And it turns out that if you have a function of exponential order and it's piecewise continuous, I made a video on piecewise continuous functions. So we've discussed that if you have both of those things, then it does have a Laplace transform. So this video is about what does it mean for a function to be of exponential order. So the definition is a function f of t is of exponential order alpha. So alpha is some number if f is of exponential order alpha if there are constants t and m such that the absolute value of f of t is less than or equal to m e to the alpha t for all t greater than or equal to capital T. Okay. And there's a lot in this definition to understand. So it takes a while to understand what this is even saying. So let's just pretend that alpha is 1. So we're interested in functions of exponential order 1. Okay. Well, what that means is that there need to be constants t and m such that the absolute value of f of t is less than or equal to m. So we need, in order to be of exponential order 1, we need that the absolute value of f of t is less than or equal to m e to the t for all t greater than or equal to capital T for some t and m. Okay, what does that mean? So let's just imagine a bunch of different capital M's and let's just graph them. So if m is 1, so this is all using alpha equals 1. If m is 1, then then this guy is just e to the t, which looks like that, right? And if m is 2, so this is e to the t. If m is 2, then it's 2e to the t, which looks like that, right? So that's 2e to the t. And if m is, m is, in this case, a positive number. So if m is 1/10, then it's 1/10 e to the t, which looks like this. So you just imagine all of these functions for different m's. So for a different m, there's a different function, m e to the t. Right. So this is 1/10 e to the t. Okay. So in order for your f to be of exponential order, when you look at the absolute value, it needs to be less than or equal to this, m e to the t, for all t greater than or equal to some capital T. So what that means, what this part means, for all t greater than or equal to t, there are constants capital T such that for all t greater than or equal to t. What that means is that eventually this is always true. This inequality always holds. So for instance, your capital F, your absolute value of f of t could be something like, okay, it could be something like this. So this, if this is your f of t, it would be of exponential order 1. Why? Because when you look at f of t here, f of t here, right? F of t is bigger than e to the t over there, but past this point, oops, past, past this point, right, this is your f of t. Past this point, the absolute value of f of t is lower than the graph of e to the t. So this would be your capital T, this t here. When little t is bigger than this capital T, so that means to the right of this capital T, the f of t is always less than or equal to e to the t. So this f of t would be of exponential order 1, because you can take capital M to be 1. Right? You can take alpha to be 1, and you can take capital M to be 1. Similarly, to be of, so if you have another function, little f, you can take little f to be, see that? Well, it's not, see, I wanted to make it look like a function. I should make this look more like a function instead of being too sloppy. So if you make your function like this, okay, this f would also be of exponential order 1, because eventually, past this point, this capital T, to the right of that, your little f is always below some m e to the t. In this case, it's below 2 e to the t. So what it means to be of exponential order 1 is that your function, there's some m, okay, it could be 1, it could be 2, it could be m equals 1/10, such that eventually the absolute value of your function is always below the graph of m e to the t. So you could have something like this. This function f would be of exponential order 1, because if you take m to be 1/10, then past this point, right, to the right of capital T, your little f is always below the graph of 1/10 e to the t. Right? This is your f. That's your 1/10 e to the t here. The yellow graph is always below the white graph. It's not always below the white graph, but it's always below the right graph when you are to the right of this capital T. So that's what it means to be of exponential order alpha equals 1. Now you could have something like, you could have a different alpha. So you could have exponential order 2, right? And then you would look at functions of the form m e to the 2t. And similarly, if you have a function where past a certain point, the absolute value of the function is always below some m e to the alpha t, then your function is of exponential order alpha. So that's the idea behind exponential order alpha. And what does it mean just to be of exponential order? So we would say that f is of exponential order if it's of exponential order for some alpha. So let's draw a picture of something. I'm not even going to say what the function is. I'm just drawing a picture of something that would not be of exponential order for any alpha. It would be something like, it's something that grows so fast that it's faster than any exponential function. So there's no m e to the alpha t that will somehow make, like if you can come up with a function m e to the alpha t so that when you graph it, then eventually it'll always be above the graph of f or the absolute value of f, then your function would be of exponential order. So if you have a function that somehow grows so fast that it always exceeds every exponential function, then your function would be not of exponential order. Sorry. So the idea is, if f grows so fast that it exceeds, like it eventually surpasses every exponential function, then f would not be of exponential order. Okay, that's the idea. Okay, so it basically has to like zoom off to infinity really, really fast. Okay, and when you have something like that, it's not going to have a Laplace transform. So what's the point of this picture I drew? So you have some function f, which I imagine going off to infinity like extremely fast, so fast that no matter what your m e to the alpha t is, you're not able to always be above it eventually. You're not able to eventually be always above the graph using m e to the alpha t. Okay. And there are lots of m e alpha t's because there's lots of different alphas, there's lots of m's, but somehow you're just, if your little f is going off to infinity so fast that you're not able to eventually be always above the graph of f using m, or absolute value of f using one of these m e alpha t's, then your function is not of exponential order. Okay. So let's give an example of an actual function that is not of exponential order. So e to the e to the t squared is not of exponential order. Okay, how do we justify this? So let's think about what that inequality, first of all, this is always a positive function. So the absolute value of f is just f in this example. But in general, we would need that f of t is less than or equal to some m e to the alpha t, and this needs to eventually be true for all little t past a certain point, right? So we need this to be true in order for f to be of exponential order. But what is going on? So this, i.e., when you divide it, right, e to the alpha t, this needs to be bounded by some m, some constant m, for all t. Well, when you have e to the t squared, and you divide it by e to the alpha t, that is going to be e to the t squared minus alpha t. Okay. And that's going to be e to the t times t minus alpha. Now this is going to go off to infinity. So this is going to go off to infinity as t goes to infinity. So there's no way that this ratio is ever going to be bounded by some constant. Right? Like there's no m such that the m, so if you imagine graphing this ratio, okay, to be of exponential order, you have to be able to come up with some m so that this ratio is always below m. But that's not what's happening, because this function, right, this guy, if you imagine graphing that, it's gonna go off to infinity. So it's going to surpass every constant m. And so what that means is that your function is not of exponential order. Your little f is not of exponential order. Okay, so what's an example of something that is of exponential order? Let's say f of t equals e to the 6t. So this is of exponential order 6. How come? Because, so is it true that for some m, absolute value is less than or equal to m e to the 6t for all t past a certain point, capital T. So for some m and some t, some capital T, this inequality is true. Well, yes, because you can take m to be 1 and capital T to be, say, 0, right? Because if you take m to be 1 and capital T to be 0, well, we know that the absolute value of f of t, that's e to the 6t, is less than or equal to 1 times e to the 6t for all t greater than or equal to 0. Actually, you could take capital T to be anything. So that shows that your function, little f, is of exponential order 6. Now, if it's of exponential order 6, then it's also of exponential order 7 and 8 and everything above 6. Because if the absolute value of f of t is less than or equal to m e to the 6t, then it's also less than or equal to m e to the anything above 6 times t. Okay. And what about a polynomial? So if you have t to the n, this is of exponential order 1. Okay, if n is an integer. If n is a positive integer. Actually, I don't think it even needs to be an integer. It just greater than or equal to 0. Because if you look at t to the n over e to the t, right, that's going to approach 0 as t goes to infinity, right, by L'Hopital's rule. So what that means is that you can take m to be 1. Okay, so let's just clarify. If you take m to be 1, then is it true that the absolute value of f of t is less than or equal to 1 times e to the t for all t past a certain capital T? Well, yes, because eventually this t to the n over e to the t is going to be bounded by 1, right? Because this t to the n over e to the t is approaching 0, so eventually it will always be below 1. So then the absolute value of t to the n is less than or equal to the absolute value of e to the t, which is just e to the t. So in general, if the limit of the absolute value of f of t over e to the alpha t as t goes to infinity is some constant, is constant. So if this exists, then f is of exponential order alpha. Okay. So I don't want to get too into the technical details, but this is a kind of easier criterion for being of exponential order. If you take the absolute value of ft divided by e to the alpha and it exists for whatever alpha, this limit exists for alpha, right, for some e to the alpha t, then f is of exponential order alpha. You don't need this limit to exist, but if it does exist, then it's of exponential order alpha. Okay, so that's the explanation of exponential order alpha.